Let's draw the Lewis structure for the ammonia molecule, as well as determine its VSEPR geometry, and finally see if it's a polar or nonpolar molecule. Start by counting up the number of valence electrons. Nitrogen is group 15. That last digit of the group number tells you the number of valence electrons. Each of these hydrogens bring in 1 valence electron. There is 3 of them, so that gives you a total of 8 valence electrons to work with. Hydrogen is less electronegative, but it does not go in the center because it can only make 1 bond. So we'll put nitrogen in the center, put the 3 hydrogens around it. Next, let's use up 2 electrons to make each of the bonding pairs to connect the terminal to the central. And we're down to 2 valence electrons after we use those 6 to make those bonds. And the remaining 2 we can put on the nitrogen, the center. They've all achieved the octet rule. Hydrogen only needs to make 2, or only needs 2 electrons to reach the duet, or the octet rule. All right, now let's look at the VSEPR geometry. The central atom is nitrogen. It has 1, 2, 3, 4 regions of electron density, or 4 effective pairs, or you hear that it has a steric number of 4. So when nitrogen has 4 pairs of electrons, or electron density that want maximum separation to minimize the repulsion, that's the key idea behind VSEPR, right? Electron pair repulsion. They want to get away to minimize the repulsion, maximize SEP. When you have 4 regions of electron density, and in ammonia's case, one of them is not bonded to another atom, but 3 of them are. So when you have 1 lone pair from a parent geometry that's tetrahedral, then that molecule is trigonal pyramidal, or trigonal pyramidal, however you want to say that, or a triangular pyramid, you can say. So let's redraw that using the line dash wedge. Got the nitrogen there. Let's put the lone pair up here on the screen. Put the hydrogen about 109 degrees. So this is going to be slightly less than 109 because of the extra repulsion by the lone pair. Okay, and the other hydrogen is coming out of here at the screen, and another one going back behind the screen. All these bond angles are approximately 107, so you can say less than 109. And again, that's because of the extra repulsion by the lone pair. Finally, let's see if this is a polar molecule. Now the electronegativity difference, or the delta chi, is 3 minus 2.1, that's 0.9. So this is a polar, these bonds are polar between the nitrogen and the hydrogen. So there's a net dipole going this way because these dipoles do not cancel out. All right, so this side might be generally slightly positive, and this side where the nitrogen is hanging out is slightly more negative. So this is a polar molecule.